Okay, we're going to continue looking at different types of inner products. This is the first inner product that we're going to look at that's not on Rn. It's on a different vector space. This one is what we call the standard inner product on M and N, so on a vector space containing square matrices, n by n matrices. The way that we define this one, so if there's two matrices in this n by n, or this space of n by n matrices here, the inner product of U with V is defined to be the trace of U transpose with V. Because it's a lengthy exercise to prove that each one of these are an inner product, we're not going to prove that this is an inner product, although that is a good exercise for you to do, for you to try out. Instead, what I want to do is practice using the inner product for the things that we care about, the norm of vectors and the distance between vectors. So here, we're doing a couple of things. I want to find the norm of U, which means I'm doing this. The norm of U is equal to the square root of the inner product of U with U, or in other words, the square root of the trace of U transpose with itself. Okay, so what I'm going to do is evaluate U transpose times U and then take its trace so that I can evaluate this. Now, if you notice, the matrix U is symmetric in this case, which means it's equal to its own transpose. So U transpose U just looks like this: 1, 2, 2, 0, 1, 2, 2, 0. This will produce a 2 by 2 matrix. So that's 1 plus 4, which is 5. And then I'm actually going to just get this entry down here. That's going to be 2 times 2 is 4, plus 0 is 4. Now, you notice I didn't bother getting these entries because I just need the trace of this. The trace is just the sum of the main diagonal entries. I could easily get these two values, but they don't matter. It's just the main diagonal that matters. So this becomes the square root of 5 plus 4, which is 9. And I get a norm of 3 for that matrix U. Okay. And the next thing that we want to do is find the distance between matrices U and V. And if you notice the way that I selected these two matrices, U and V, they look very, very similar to each other. In fact, they only differ at one entry, and they differ by 1 there. Down here there's a 2, down here there's a 1. Because they're so close to being the same matrix, you may expect the distance between them to be a small number, or a relatively small number. So we're going to test that theory here. So again, if we want to find the distance between U and V, it's the norm of U minus V. So I'm going to compute U minus V. U minus V is equal to, well, I'm just going to come up here and do this manually. 1 minus 1 is 0, 2 minus 2 is 0, 2 minus 1 is 1, 0 minus 0 is 0. So I get 0, 0, 1, 0. There's the difference between those two. Okay, now remember, the norm is going to be the inner product of U minus V with itself, U minus V. So that means I'm looking for, by definition, the trace of the transpose of this matrix times itself. Well, the transpose of this matrix would be 0, 1, 0, 0 times itself, which is 0, 0, 1, 0. And, sorry, I meant to write this. This is U minus V transpose times U minus V. And computing this manually, my first entry I'm going to get 1, followed by 0, and then 0, and then 0 again. So the trace of this matrix is 1 plus 0, which equals 1. These are the two values that I needed. 1 seems like a relatively small number. In fact, it's the difference between the only entry that these two matrices differed by. Is that true in general? Not really, but it does kind of fit our intuition that we expected a small number here. Okay, let's go ahead and move up to another inner product. We're going to look at a couple of inner products for polynomial spaces, Pn. The first one, we're not going to do anything in this lecture with this, but you may in the homework see some problems where you're working with this. This is called the standard inner product on Pn. If I have two polynomials in Pn, so nth degree polynomials, P and Q, I define the standard inner product of P with Q this way. Now, if you notice, this is actually just the dot product, but applied to the coefficients of P and Q. You notice there's no x's here. I'm just using the coefficients a0 through an, b0 through bn, multiplying corresponding coefficients, and then summing the results. It's really just the dot product, where instead of vectors in Rn, we have coefficients on polynomials. So there's nothing that unique about that one. Another inner product which has some interesting applications is what we call the evaluation inner product on Pn. Now this one is somewhat similar. It also kind of looks like the dot product, but we're not using the coefficients on these polynomials this time. What we do is we take the two two polynomials, and then we also take a set of n+1 numbers, x0 through xn. That's a total of n+1 real numbers, and we call these values sample points. And then what we do is we plug them in to both polynomials. We evaluate the polynomials at each one of those sample points. That's why we call it the evaluation inner product. Once we've done that, we do something similar to what appears to look like a dot product. We take P of x0 times Q of x0. Remember, you've evaluated both of these. These are both real numbers. P of x1, Q of x1, all the way down until we get to P of xn, Q of xn, and we sum all of those. So we're going to use an example to illustrate this. This is a couple of polynomials from P2. Because we're in P2, I should have a total of 2 + 1 sample points if I want to use the evaluation inner product. I'm going to use these sample points, -1, 0, and 1. So I need to evaluate P of -1, P of 0, P of 1. I also need Q of -1, Q of 0, and Q of 1. So a total of 6 values that I'm going to need in order to compute this inner product. P of -1. Notice if I come up here and plug -1 into this, it becomes 1 minus 3, which is -2. In fact, I get this is an even function, so P of 1 would also be -2. And then if I plug a 0 in for x, I get a 1. Okay, coming over to Q now. If I plug a -1 in for Q, this becomes -2 plus 1, which is -1. Plug in a 0, and the whole thing goes to 0. Plug in, excuse me, a 1, and I get 3. So that means that the evaluation inner product of P with Q is equal to -2 times -1 plus 1 times 0 plus -2 times 3. Okay, so this would be 2, that's 0, and this would be -6. 2 minus 6, we get -4. Okay. Just wanted to point this out too. We got a negative number, which is absolutely okay. You can get any real number out of a dot product. The only time that the result is required to be, or is always going to be non-negative, is if I take the inner product of a vector with itself. But this is an inner product of two different vectors, so there's no need to assume it's going to be positive. Okay, one more inner product that we want to look at here, and then we're going to talk about one more theorem, and that's going to wrap up 6.1 for us. So this is a really, really important inner product in many areas of math that would come after linear algebra. And it's going to be kind of the only example that we look at that requires you to know some calculus. So this one, we're looking at an inner product on the space of continuous functions, specifically functions that are continuous on the closed interval AB. So if we have two functions, f and g, that belong to this space, that means they're continuous on that closed interval. We define this as our inner product. It's the integral from a to b of f of x times g of x dx. And that integral we know will be defined because these functions are continuous on the interval that we're integrating over. Your book walks through a proof of why this is an inner product, so I'm going to let you look at that over on your own as opposed to using the time to go over that here. What I want to do is just practice using this inner product. So again, the inner product gives us a sense of size or magnitude of a vector, and in this case it's going to represent like the size or magnitude of a function, and then we're going to find the distance between these two functions relative to this inner product. So let me start with the this guy. Oh, and you know what? I left something off here. We're going to consider these to be functions in the vector space C0, 1. You can't do anything unless you have a specific closed interval that we're talking about, because those become the limits of integration. So if I want the norm of f, that's equal to the integral from 0 to 1 of f of x times f of x. And then we need a square root of that whole thing. Notice this dx in there. This is the inner product of f with itself, and that's what we use when we're finding a norm. So this would be the integral from 0 to 1 of x squared squared, which is x to the 4th dx. This the integral here, we get x to the 5th over 5. Evaluated from 0 to 1 gives me 1/5. So this comes out to 1 over root 5 as my norm. Okay, so that's what we would think of as basically the size of this function. Distance between f and g. What is the distance between x squared and 2x? Well, again, remember what we're looking for is the norm of f minus g. That is, we're looking for a square root. Now, I'm going to do, because this is going to become f minus g times f minus g down here. So let's evaluate that. F minus g, that's x squared minus 2x times x squared minus 2x. I'm going to multiply that out. That's going to be x to the 4th minus 4x cubed plus 4x squared. X to the 4th minus 4x cubed minus 4x squared dx. Okay? Evaluating this, I'm going to get, let's see, this is going to become square root of x to the 5th over 5 minus, this will become x to the 4th minus 4/3 x cubed from 0 to 1. Didn't quite leave enough space here. This is equal to the square root of 1/5 minus 1 minus 4/3. Let's see, what do we get from here? Oh, I think sorry, I made a mistake here. This should have been a plus. I don't know why I made that a minus. This would be a plus as well. That would be a plus as well. So see, -1 plus 4/3 is 1/3. 1/3 plus 1/5 would be 8/15. So this becomes the square root of 8/15. And yeah, you could or simplify this radical and do what you oftentimes do, but I'm just going to leave it in this form. So this would represent the distance between those two functions. Can't visualize that the way that you can a distance between 2 points or 2 vectors, but it's how we're defining that distance. All right, last thing to cover, and this will be what we finish this video with, is a few theorems on working with inner products algebraically. Notice some of these properties look similar to the properties that we defined our inner product with. For example, property B looks similar to the additivity property, but it's not, because the let me go back to the page where we define that. Notice here, additivity is, the u plus v is showing up in the first component, not the second. Here we have a sum of vectors in the second component. Sometimes we say that this is additive in the second component, but this is going to also be true, and it's just something that we would have to prove. So 5 properties here, all really useful for algebraically working with inner products, but the proofs are all fairly straightforward. We're just going to look at the proof of one of them for E. Notice this is similar to the homogeneity property, but the difference is that K is not being brought out of the first component like it is in the definition of an inner product. It's being brought out of the second component. The K comes out. So we need to prove this using only the axioms that define an inner product. I'm going to start on the right side and then get to the left side. So starting on the right, the inner product of U with KV, I can switch the order of these two components using my symmetry axiom. That puts the K in the first component instead of the second component. Now that the K is here, I can use homogeneity to bring it back out, so that I end up with K times the inner product of V with U. And then I can apply symmetry one more time to the two components here to put them back in the order of U and V. This establishes that result E. The other results here can be proven in a similar way. We really just need to be using the axioms of an inner product. But that's going to wrap up 6.1 for us, and next week we'll move on to 6.2.